Physics 1 Lab 2 report covering the motion of a falling object using the forces of gravity and drag. An object is recorded starting from rest, dropped, and moving toward the ground with increasing velocity due to gravity, analyzed using the software tracker, and 2 models are created using glow strips to predict the object's motion, one with drag and one without drag. The model with drag has an excellent prediction of the object's motion that almost perfectly matches my experimental results. Without drag was slightly different. The purpose of this lab is to further examine the motion of a falling object by understanding the constant force of gravity and non-constant force of drag and their effects on the system. This lab utilizes Newton's second law, which states that F net equals change in momentum over change in time. This is used to update the velocity and position of the ball as it falls. Since the velocity changes as the ball falls, F net does not equal 0 until it reaches terminal velocity. This lab also demonstrates Newton's first law, which states that an object at rest remains at rest and an object in motion remains in motion at constant velocity unless acted upon by an external force. Gravity and drag are the external forces changing the ball's velocity. I will discuss terminal velocity later in this report, where the net force is equal to 0 and Newton's first law is in play. These are the formulas I used in this lab: the force of gravity near the Earth's surface, or the weight force; the force of drag, Newton's second law in the form of the velocity update and position update formulas, and the formula for initial velocity. The system in the experiment was a soccer ball, and the surroundings include everything else, like me, the Earth, and air. I calibrated a tracker using the known diameter of the soccer ball, 0.22 meters. I used a standard coordinate system with positive x hat to the right, positive y hat up, and positive z hat toward us. Here's the tracker video. Initial conditions. The ball's mass was 0.45 kilograms. Its initial position from tracker was 6.65 times 10 to the negative 9 meters y hat. I found the ball's initial velocity by taking the second recorded position in tracker minus the initial position divided by delta t. This gave an initial velocity of 0.01098 meters per second, negative y hat. Time started at 0 seconds, and I chose delta t to equal 0.01 seconds, so I have a very small time step and a more accurate prediction. Little g is the gravitational acceleration near the surface of the Earth and equals 9.8 meters per second squared. J hat or y hat points in the upward direction. B is the drag proportionality constant. In this class, we were told to use trial and error to find the most accurate predictive results compared to the experimental results. In my case, I found 0.25 to work best. Inside the while loop. The last time recorded in tracker was 0.533 seconds. Force of gravity on Earth, or the weight force, is equal to an object's mass times little g in the negative y hat direction. 0.45 kilograms times 9.8 meters per second squared gives us the constant force of 4.41 newtons in the negative y hat direction. We know this force is constant because it is the same no matter the object's position, velocity, or time. Since mass is constant and little g is constant, so is the force of gravity. When calculating F net, however, weight is not the only factor. In this case, we must account for the force of drag acting on the ball. Drag force is the force of air resistance on an object in the opposite direction of an object's velocity. In this case, the drag vector points to positive y hat, since Fg points to negative y hat. For this lab, we calculate drag as it is proportional to velocity squared, but in the opposite direction. In Go script, you cannot square a vector, so I squared the ball's speed, which is the magnitude of its velocity, and left out the negative sign as the magnitude was in the positive direction already. F net is the weight force plus the drag force. Like Lab 1, this lab emphasizes the use of Newton's second law to update the ball's velocity and position. First, we update the velocity using the velocity update formula. V final equals V initial plus F net over mass times delta t. After that, we update the position using the position update formula. R final equals R initial plus V average times delta t. We use the new velocity as the average velocity. To visually represent the forces in the glow strip model, I added arrows. The orange arrow represents the weight force and the blue represents the drag force. To find the length of the weight arrow, I multiply the weight force by the arrow scale, which is set to be 0.5. For drag, I multiply the drag force by the arrow scale, each arrow to help us set the ball's position. Comparisons. The model with drag did an excellent job at predicting the motion of the ball. The only noticeable difference is in the last data point. This could be due to an increase in air resistance, a different external force, or the frame not being the exact moment the ball hit the ground. It could also be a tracking error. Besides that, the prediction was very accurate. The model without drag did not do as well. This shows the importance of accounting for air resistance in real-world applications. The model without drag fell further than the model with the drag in the same amount of time because F net was only considering weight. Here are the video comparisons. Based on Newton's second law, since F net is a constant force, change of velocity is constant, but when you add drag into the equation, F net is no longer constant since drag force depends on the instantaneous velocity of the ball. What does it mean, velocity versus time? Without drag, F net is constant and velocity increases in the negative y direction at a steady rate, as shown in the velocity time graph. With drag, you can see the velocity start to flatten out and slowly become constant at its terminal velocity, where the drag force and weight force have the same magnitude and result in a net force of 0. None of my models seem to predict a terminal velocity since the ball did not fall for long enough. However, when I increased the end time in the while loop, I could see the point where the ball would reach terminal velocity. This is the point where, since F net equals 0, Newton's first law can be seen, an object in motion remaining in motion at a constant velocity. What if the ball was initially thrown downward rather than falling from rest? The terminal velocity would still be the same. It would simply be reached at an earlier time than if I was starting from rest. The ball dropped from rest, like my experiment, would reach a terminal velocity at closer to 4 seconds, while the ball thrown at a velocity of 15 meters per second y hat would reach it at less than 0.4 seconds. For my experiment, terminal velocity happened to be 16 meters per second negative y hat. Terminal velocity is still the same since force of gravity is constant and does not rely on velocity. Force of drag does, but this just means it will release terminal velocity in an earlier time if it is thrown instead of dropped from rest.